Now, to the course website, I typically post the rules and guidelines for doing oxidation states. Now, I'm going to be honest with you, the rules I post are actually a bit longer than the real rules. And the reason I say it's a bit longer is that some of them are actually just kind of consequences of other rules. So let's go through those rules. First of all, if we have a compound, a molecule, the sum of the oxidation states has to equal the overall charge. What this is saying to us is that if we add up all the protons and all the nuclei and we subtract out the number of electrons that each atom has, we should end up with a net charge. So if we have an atom with four extra electrons and one with 3 underneath, we should end up with an overall excess of 1 electron. Second rule, the more electronegative element takes the negative charge if you have 2 elements bound to each other. This is more of a statement of definition. If we have 2 elements with different electronegativities, by definition, the more electronegative element takes the electron. Because of that, we had the additional rule that fluorine is always -1 if it's not bound to itself. And the reason we had that rule is that fluorine is the most electronegative element on the periodic table. So if it is bound to anything, it's always going to win, and it's always going to take the -1 charge. We also get the rule get the additional rule that a metal bound to a nonmetal, the metal is going to take the positive charge, and the nonmetal is going to take the negative charge. Metals, by definitions, have low electronegativities. Nonmetals, by definition, have high electronegativity. So if you've got them bound together, you get the 2 other rules. The metal has to be positive, the nonmetal has to be negative. So what are some other rules we have to consider? Well, if you have diatomic gases, they have a 0 oxidation state. The reason behind this is that if you have 2 elements pulling on electrons and they're equally strong, equally electronegative, there's no way one can take an electron from the other. So we end up with 0 oxidation states. We also have the rule that if you have a lone atom in a chemical formula like Ag solid or F- aqueous, the charge you see on that atom is the oxidation state. Again, this is more kind of a statement of definition. If you have a silver +1 atom in solution, Ag +1 AQ, it has to be +1. You're specifying the charge, and the charge in this case is going to equal the oxidation state.